Okay, welcome to this lecture on image transformation. Okay, in our last lecture, I introduced you about the Euclidean transformation, where the first type of Euclidean transformation, which was translation, rotation, and scaling. This is another type of Euclidean transformation. In Euclidean transformation, the important point is these angles and lengths. These remain constant. Okay, so you should note this point. This is important in when you do rotation. So in rotation, now this is interesting. Like rotation is related to somehow like angle transformation, and when I say that angle remain constant, so this is somehow contradiction, but this is angle inside the object and not angle of the along the rotation axis. Okay, so this was already discussed in our last class, and then you saw this formula for translation, and then we defined a translation matrix, where for the sake of simplicity you can consider this matrix and you can multiply the rotation matrix with each point. Okay, and then you will get a translated image. Okay, now the next important transformation is rotation. Okay, so let's take an example. Suppose I consider this rotation in 2D. Okay, this is not in 3D, but it's a 2D rotation. But however, the concept of 2D and 3D is not that different. You just need to add a third axis. Okay, let's say we have this point. Okay, and we want to rotate this point along the center point. Okay, so this is our vector for this point, and the angle of this vector is phi. Okay, the point is represented by x and y points, x along x-axis and y along y-axis. Clear? Okay. Now I think from your metric school maths or physics, you might have already resolved this vector into its component, like x component and y component, and I am sure you already know this, that the x component is equal to the vector multiplied by the cos of the angle, and similarly the y component is equal to the vector multiplied by sine of the angle. Okay, are you all convinced about these things? Okay, fine and good. Okay, now we rotate this angle. Okay, and we get this new position, which is x prime and y prime. This is the new point, and it has the rotation angle theta. Okay, and now we want to resolve this vector into its component, x and y component, and as we did with the previous, this is the same vector, the length is same, this is to be noted. Okay, the length is same. So, and now the whole angle with the x-axis, this is phi plus theta. Okay, so in this example here we Okay, in this component we had this theta, but now the theta, this is this whole angle, okay, which is theta plus phi. So it will be r cos, and instead of theta we have this theta plus phi. Is it clear?
Yes.
Okay, and similarly on the for y component we have this whole angle which is phi plus theta. Okay, so we have y prime is equal to r sine and phi plus theta. Clear? No confusion? Okay, what we are interested in, actually we want to define some metrics for rotation, because for translation it was very easy metrics, but we want to know whether we can formulate this rotation with some simple representation. Okay, so this is actually our objective. Okay, so we already know that the x component for this r vector is equal to r cos phi, and for y it is r sin phi. Okay, and for the rotated vector, which is r, but the difference is angle. Okay, there is no difference in the length, so the r is taken the same, and the angle is combination of these two angles. Okay, and now we consider some trigonometric identities. Okay, this is like maybe the metric or first year trigonometry equations. So I myself, I had forgot these equations, but you can just look back those books and you will find these formulas, where sin phi plus theta is equal to sin phi cos phi plus cos phi sin phi, and then the minus symbol for this minus symbol in sine case, this is the same, but then in cos case this is opposite. Okay, when you have positive sign here, so you take negative sign, and when you have negative, so you take positive sign. So these are the important trigonometric identities, okay, which we can use for simplification of our equations. Clear? Okay, now we can expand this equation. Okay, we have this equation, and we can use these trigonometric identities and can expand it like this, and then we can also expand these identities, okay, like this one. Clear? Okay, no confusion so far? Okay, so everything is simple. Okay, now you might have guessed that I have colored these values like r cos phi, which is already equal to x component of the vector, and then sin phi, it is equal to r sin phi, it's equal to this y component. Okay, so we have these different quantities. I have just colored these for like, so that you might have intuition for this. Okay, so we replace this r cos phi with x component of the vector before rotation, okay, and r sin phi with the y component before rotation. So simple. Okay, this r cos phi, this value is replaced by x, and this is replaced by y sin phi, okay, and this is replaced by x, and this is replaced by y. Okay, so now what is this x prime and y prime? This is the point. The x and y represent the point after rotation. Okay, and these values, this x and this y, these are the values before rotation. Okay, so we have this point here and we have rotated this vector by this angle theta. So what's the equation now? When we want to know the final position of the point, so we can consider this formula. Okay, the angle is given, and then we can use this formula to get the final position. Clear? Okay. Now we are in a position to write this same equation in a matrix form. Okay, so you can either use the matrix algebra from your 10th class or question. What?
The sin pi plus theta, there was the sin pi cos pi plus cos pi sin pi, but we write in the base matrix prime equal to r cos pi.
Where and the identities are here or
negative or positive values.
These, yeah. Okay, in case of cos theta, the signs are opposite. Okay, but in case of sine, the signs are same. Okay, when you consider cos, so the signs should be opposite. Here I have plus, so here the sign is negative, and here I have negative, so the sign should be positive. So these are like these formulas. We can prove this, but this is like 10th class work, so we can skip it. However, for sake of your to convince yourself, you can just go through these trigonometric identities. Okay. So just look again to this equation. This is like our final position. These are these trigonometric values, and x and y are the original position. Okay, if I make some mistake in these symbols, so please let me know. Okay, so now this is the position after rotation. Clear? And this is the original position before translation, and this can be the rotation matrix. Okay, so and this was the previous equation. Okay, so you can just multiply this equation with this one and you will get these quantities. Okay, clear?
Yes.
And for y you can multiply this with this vector, so you will get this quantity. Okay, confusion or you are
Yes, the sign value, because
okay.
the previous slide
Okay.
X contains the minus sign and the y plus sign. X cos theta minus sin theta, x prime value was, and y
For-
prime was x cos theta plus minus sin plus cos sin theta side, and x value was x prime value was cos theta minus sin theta.
Okay. So then we need to replace these values maybe. Okay. Like I have taken plus symbol here, minus. So it can be replaced with plus and it should be minus. Okay,
Yes, sir.
but I will have to confirm this because as I remember, so the rotation matrix is like this one. So I might have made some mistake in the previous these trigonometric identities as far as these symbols are concerned. Okay, but that is not the problem. Like the basic concept is the same. Okay, these are just like symbols. Clear? Okay, so if you knew this rotation matrix, so I hope it will help you in your research. Okay, you people might already using these rotation matrices, and this is important. Okay, for image processing people as well as for graphics people. Okay, is there any further question? Huh?
So how is this constructed from the equations, the rotation matrix?
Okay, good point. How it is constructed from the rotation matrix. Good question. You can just like in this equation, this is okay. This is like one side of the equation. Okay, so one side equation is represented by this vector value. Okay, and now this is second part of the equation. So you divide this right side into this 3 by 3 matrix and one vector. Okay, when you multiply this 3 by 3 matrix with this one, so you get this equation. So you can either write this rotation using this equation, or you can use these matrices, and so these are actually the same. You can either extract this equation from these set of matrices. Okay, like one side, this is simple. You multiply this matrix with this one, and you get this equation. This is simple. But now maybe your
He means to say that how we have created these two matrices from the given two equations. So we have read in matrix that the coefficients.
yeah.
For example, here V is the coefficient of the cos theta,
Yes.
and W is the coefficient of the sin theta in the first equation, and in the second, in the Y equation, V is the coefficient of the sin theta, and W is the coefficient of the cos theta. We separate the coefficient in separate vector and the remaining in the other vector. So we
Yeah.
can find it. This
So,
was there in the
it was actually answered your. I was thinking that he is adding to the question, but he was actually answering your question. So V and W, these are the coefficients, and x cos theta and sin theta, these are the variables.
Yes.
Okay. So from one side, I think it's simple, like you multiply these two matrices and you get the equation. But if you just think how we compute or we separate this equation into two matrices, so again it is not that difficult to think. You consider these coefficients P and W, okay, and you consider this as the variables. Okay, fine. Okay, now the next type of transformation is scaling. This is not very difficult, but there are some more things to learn during this discussion. Okay, so scaling is simply resizing of an image. Either you enlarge the original size or you decrease the size. So this is the simple definition of scaling. Okay, and here too you can, like this is scaling means multiplication. So multiplication, when this multiplication, the multiplication factor is more than 1, so it is enlarging the size, and when it is less than 1, so it is decreasing the size. So this is just multiplication, and the equation will be, this is the final position, this is the original position, and this is the scaling factor along x-axis, and this is the scaling factor along y-axis, and this is the y component. So this is the y component. So this equation is simple. Okay, now the difficulty I think may arise how we get this matrix. Okay, so again, like when you multiply this row with this column, okay, you get this value. Okay, and when you multiply this row with this column, you get this equation. Okay, so again this is like this 3 by 3 matrix. So if you look, whether it is scaling or whether it is rotation or whether it is translation, always we consider this 3 by 3 matrix. Okay, so it is like a general representation for any type of transformation. Okay, any type of transformation can be represented by this 3 by 3 matrix, but then for every transformation you change this transformation matrix. The dimension is same, but the values become different. Okay.
So why we consider the 3 by 3? Why not the 2 by 2?
In last lecture, I had asked this why this 3 by 3 matrix. So usually in computer graphics, each point is 2D point is represented by 3 what we should call it coordinates. Okay, and this additional coordinate is used for homogeneous coordinates. So like there are some mathematical formulas and mathematical set of equations, and we want to use those equations, so we modify our representation so that we can fit into that framework. Okay, so when we consider a 3D coordinate system, so in that case we will represent 1 point by 4 by 4 matrix. Okay. Okay, so now for this scaling we have this simple matrix. Okay, this is not very difficult. Okay, but I want what happened? Okay, start. Okay, so I don't know how. Have you already heard about interpolation? Interpolation. You? But you are sleeping. Okay, you have already heard this word interpolation. Okay. You? Okay. Okay. So.
Sorry, continuously we tried in scaling and stretching.
Yeah, stretching is next. This is like shear. We have another transformation that is called shear transformation. So we are discussing that after this topic. I am not sure whether stretching is the suitable word, but we will see. Okay.
So the scaling is your object image will scale by a number of pixels you are.
Okay, this is what we are interested in, and we are discussing this. Okay? Just wait for a moment. Okay. Let I have this image, and okay, I have a small object inside this image. Okay, this is a 10 by 10 okay, this is an 11 by 10 image. Okay, and I have this object inside this object. Now, okay, this is this object. Clear? Now I want to rescale this image, and in this rescaling I increase the size by a factor of 2. Okay, simple. I have enlarged an image, but now I am interested what is happening to the pixels configuration. Okay, so when it is a factor of 2, then these coordinate positions, I just multiply this with factor of 2. For x I take double of x, and for y I should take double of y. Clear? Okay, so now, okay, I have this 10 by 9 image. Clear? Now I am interested in the positions after rescaling. Okay, so this position in this image, its coordinate are 1 and 3. Okay, so after rescaling, this should be 2 and 6. No, okay, only I'm talking about this pixel position. This is 1 and 3. The coordinate in this image for this pixel is 1 and 3. So after rescaling by a factor of 2, the position for this pixel will be 2 6. Okay, so this is 2 and this is 6. Okay, so I can take this as 1, because here it was 1, so here I'm taking 1. Okay, and now for this 1 and 4.
2 and 6.
Oh, sorry. This should be 2 and 6. So it will be here, and I can take it as 1. Okay, and now for this pixel position, it is 1 and 4, so it will be 2 8. So 2 8 here.
Yes.
4, and here it will be 1. It is 1 and 5, so 2 10. So 2 10. Okay, and the original value is 7. Okay, now for this, okay, here this is 2 and 3, so it will be 4 and 6. Okay, 4 and 6, and the value is 1. And for this second, for this is 2 and 4, so it will be 4 and 8. Clear?
Yes.
Okay, 4 and 8, and it will be 4. Okay, and this pixel position 2 and 5, so 4 and 10. Okay, so this is 7, Okay, and here it's 3 and 3. So it will be 6 and 6. 6 and 6, and it's 1. And then for this 4, it's 3 and 4. So 6 and 8. 6 and 8. 6 and 4, and this is 6 and 10. Okay. Now I have this pixel position where I don't have any value, and I have this pixel position where I don't have any value. Okay, so actually the new object boundaries are, these are the boundaries. Oh, I don't know.
No, it is for 5 by 7.
Okay. Okay, so now the image, the new object, the image size is same, but actually I have increased the size of the smaller object inside this image. But my point is, here I have these pixel value, this one, this one, this one, this one, this one, and this one, and this one, and this one, and these are the pixels having no values. Okay. What?
But the picture is also translate from
Yeah.
Actually, this is not the scaling. Actually, we multiply the number of pixels in X and number of
Yeah.
pixels in Y, and then replace the attached pixel.
Yeah. So the actual scaling, like this was in my mind, but I was just taking it, like I was interested in this interpolation. Okay, so for that purpose I explain this in this way. Actually, like the position should be, the original position should be the same. Okay, but I am interested in these empty pixels from this rescaling. Okay, this was the actual motivation for this type of explanation. So what should happen for these pixels? What?
Never pixel value is image.
Okay. Do you think we have some problem or no?
Describe my
What?
the one chimney character doesn't the one point two
Yes. Because the scaling factor is 2. So that's why. Okay. So what's the problem?
So same object, different objects. Division of the same object.
Okay, so we need to fill these blank spots. Okay, we need to fill these blank spots, and then there are different techniques to fill these. Either we can okay, so for this part we can either consider 1 or 4. Okay, here the actual pixel is 0, but if we consider 0, so it will be not the original object. So we can either replace this by 1 or 4 or average. Average of 1 and 4. Okay. Okay. And okay, so there are these different techniques to fill these blank spots. Okay, and this is interpolation. So constructing new data points from existing data points. We have existing data points and we want to create new data points based on these existing data points. Okay, so there are different types of interpolation. One is nearest neighbor interpolation, where you consider the most nearest pixel to an empty pixel and replace the value by that pixel. Okay, for example, in this case Okay, if we have some value at this position and another value at this position, and we want to fill these 3 pixels. Okay, so then maybe taking average at this position, average of these 2 pixels, and replacing the position of this pixel by that average value, that I don't think it would be a good replacement, because if here I have, let's say, 1, okay, and here I have 20, so the average value will be 10, but this neighbor, its value should be more close to 20. Okay, so these are there are different interpolation techniques, and from experiments then it would be possible to know the difference between these different types of interpolations. Okay, this interpolation was not part of our current lecture, but I thought it's a good position to explain this concept. Okay, so I can either give you these different types of interpolation as an assignment. You can just search web and look for these different types of interpolation. Okay. Okay. Haven't you used this interpolation so far? Okay. Do you use mesh as your application? No mesh. So then what do you, for your object representation, what you do? Because in computer graphics,
There are different functions available.
but however your objects are in the form of meshes, surface meshes.
Already available function could be like J object.
Yeah. But I mean downsampling meshes and upsampling meshes. You haven't used it so far. Okay. Good. Okay. The next transformation is called share. Okay. So share is actually stretching an object either along x-axis or along y-axis. Okay, but this stretching force, it shouldn't be vertical to the axis. Okay, so if I have this object and if I apply a vertical force opposite to the surface or in the direction of this surface, so this wouldn't be considered as shear, but the force should be along an axis, not vertical to the axis but along axis. Okay, like we apply some force in this direction and the opposite force on the opposite surface, or force along the surface on one side and force along the opposite direction on the other side. Okay, so this is like, we can call it as stretching. This is then shear. Okay, and then we have these matrices for shear. So for shear along the y-axis, we have this representation where the y position of the component of the point remains same, and the x component, the length of the x component is increasing, and along y-axis the y component size increases and the x component remain constant. Okay. Okay, now we have I think the most important transformation in image processing, and that is affine transformation. Okay, this is also called affine map or affinity. Okay, so in translation, the shape of the object remain constant. There is no change in the shape, there is no change in the angles, there is no change in the length. Okay? In rotation, there is no change in the angle inside the object. A square object after rotation will always remain square, and then the length also remains constant. Okay, but as we discussed in scaling or in shear, the length doesn't remain same. Okay, so in affine transformation, the shape of the object doesn't remain same. Okay, but then there are some aspects which remain constant. Okay, for example, in affine transformation, the parallelity of the lines remains same. In object, the lines in an object remain, the parallel lines remain parallel after transformation. Okay, for example, okay, this is the object and this is the object after transformation. So the shape is not the same, but this line, okay, this line and this line, these are parallel in this object. So when it is parallel in this object, in the object after transformation, then we say that this is affine transformation. Okay, similarly, lines here, this line, okay, you can take this line and this line, these are parallel in this object. So this line is this one here, okay, and this line is this one here, and these are parallel. Okay, you can let's say that you have some line here and another line inside the object is here, and these are parallel in the original object, and if these lines are not parallel after transformation, then we cannot call it as affine transformation. But if every line which is parallel in the original object is also parallel in the object after transformation, then we call such transformation as affine transformation. Okay? Okay, the next point is angle. In affine transformation, the angles changes. Okay, in translation or rotation, the angle remain constant, but in affine transformation, the angle changes. For example, here we have this angle which is a right angle, but here it's not a right angle, and similarly here the angle changes. Okay. Okay, then there is another point in this transformation, and that is ratios. Okay, so for example, when I take some point here, okay, so and this is my line in the object before translation, and this is mid point, and this same line and the object after transformation is this one. Okay, so this point is here, and then this is also midpoint after transformation. Okay, so this is also an aspect of affine transformation, that the ratios will remain same. The length can change, but the parallelity and the ratios will remain same. Okay. Okay, I already mentioned that in affine transformation, the length and angles, these cannot be preserved, but the parallelity and the ratios remain constant. Okay, so these are this transformation is very important transformation in image processing in the context of pattern recognition. Okay, we say that like the objects during different acquisition environment, they can change its shape. Okay, but when you recognize an object, whether this is the same object or it is a different one, so you also need to consider these different transformation, whether we can say that these are two different images, but we have to look whether this is actually a translated form of that same object. Okay, or whether this, we will say that these are two different objects, but we also need to look whether this is some rotated form of that original object. Then you cannot say that these are two different objects. This is actually the same object with some form of transformation. And we also need to look whether this is some elastic object and there has been caused some affine transformation. So if an object has gone through affine transformation, so it will look totally different, but we need to look whether this is these difference has been caused by transformation or these are really two different objects. Okay, so this is like the some important points if you are working in pattern recognition. Okay, in pattern recognition you need to make groups of different objects. Okay, so you cannot put same object in different groups if these two objects are actually the same but have gone through some transformation. Okay, so like you can think over different situations where same object can go through either rotation or maybe translation will not be that important, but this rotation and scaling and shear and affine transformation, these transformation can make a problem really challenging one. Okay?
Yes.
Okay, so I think this is enough for today, and you should go through these slides again, and then if you have some questions you can ask. Okay?
Yes.
What?
Stretching.
1 minute.